So this is a discussion on the material in section 3.6. So we're going to be talking about distance functions and speed and velocity. And so, yeah, so several of the problems have talk about, have a function which gives you the position of some kind of particle or like a car or something that's moving. And then we have a few definitions here. Okay, so then we talk about the average velocity, and the average velocity is given just by, we've seen this before, like the average slope, or right here. So it's S of A. So let's say we want the average velocity from A to some point to A plus delta t. So we just look at the slope. We measure S of A plus delta t minus F of A divided by the time. And the instantaneous velocity is just the derivative of S of A. Okay, so one thing before we continue, I just want to emphasize here is that, okay, so the velocity can be positive or negative. Okay, so velocity actually has two components to it. So it's actually its magnitude, its size, but also direction. So we can move to the left or we can move to the right. So when we move to the right, we typically say that the velocity is, because we think of going to the right as positive. And so going to the right, so if the velocity is positive, it means we're moving to the right. If the velocity is negative, it means we're moving to the left. And typically, an upward velocity means that we're going up, and a downward velocity means that that the particle is moving down, or whatever is moving down. It doesn't actually have to be, it's arbitrary. I think I once had a teacher in college who decided that left was positive and right was negative. So, and it's perfectly fine as long as you're consistent, but we're not going to do that because it just gets confusing. Okay, so let's just look at this one. So again, let me just repeat here. So we have these distance functions, S of t, and the first derivative is the velocity. The velocity can be positive or negative, and if it's negative, the particle is going down, and if it's positive, the particle is going up. And in this case, and if you've had physics, you have a little bit of an advantage here. So that's the kind of the typical distance function you see for like a particle being thrown in the air or being dropped off of something. So 1/2 gt squared, where g is just the acceleration, minus 32 feet per second squared. V naught is the initial velocity, and S naught is the original position. So in this case, it says write the function. So right here, write the function to represent the height at some point in t. So all we're going to do is we just substitute the given values here. And so in this case, we say that the initial velocity, we're throwing something off a cliff, so it's moving down. So we're saying the initial velocity, it has to be negative because this ball is going down. And then we say the acceleration is minus 32 feet per second squared. And so we just plug those into this formula right here. G is minus 32, V naught is negative 20, and the initial height is 450 feet above above land. So we get this distance function right here. So after any point time in t, I assume that t is in, it doesn't actually say, so t is in seconds here. So S of t is equal to minus 16 t squared minus 20 t plus 450. Okay, so we're going to see a graph, or maybe it's a little difficult to read. Okay, well, let's look at the average velocity in the, so t is seconds. So the average velocity would, after 3 seconds, again, we've seen this before, maybe more at the beginning of the course. The beginning of the course really wasn't that long ago, but yeah, as we just measure the slope going from 0 to 3 of that function right there. Okay, so it's just, the S of 3 minus S of 0 divided by 3 seconds. And I'll let you verify that turns out to be negative 68 feet per second squared. Right? So we know S of 0 is just 450. So you can just plug in 3 into this function right here and then calculate that. Okay, so then the instantaneous velocity. Okay, so let's just look at the instantaneous velocity after 2 seconds. And so you actually have to take the derivative, and so the derivative of S of t, well, the 450 goes away, so you get minus 32t minus 20, and now you just plug in 2 in there, and you're going to get the instantaneous velocity is minus 84 feet per second. So yeah, when we talk about velocity, we were talking about a rate. So we want to know how many feet per second is it. In this case, so it's negative, so it's going down. And then there's this, I don't know how useful this graph is right here. So the blue graph is actually the distance function, right? So the blue graph is the distance function. It's a little bit short, kind of small. So, kind of pretty impressive, I guess. Drawing by hand, I guess. Okay, so the black line, there's the tangent line at t equal to 2. So you see it's near t equal to 2, that straight line, the one that's drawn in the black font, the straight line is really very, very close to that blue curve, which is a parabola. So when I say close, it's equal to 2 seconds, I'm talking about like 2.1 or 2.01. So the tangent line really approximates the distance function very, very close to t equal to 2, right? Because that's what we do. We took we found the velocity or the derivative at t equal to 2, and then the average slope. Well, that line doesn't really get that close to the not nearly as close as the tangent line at t equal to 2 is actually identical to the curve. So the average slope kind of approximates the curve, but not nearly as good as the tangent line. So okay, so that's just our first introduction. The important thing to know here is that if you're given a position function, that the first derivative is the velocity. The velocity is in terms of is a rate, so it's got to be like distance per time, and that the negative typically we have a direction as well. Negative means we're going down. Positive means we're going up, or left or right. Left means negative. Right means positive. Okay. So that's the important thing. So probably if you have head physics, you learn something about this. Velocity has magnitude and direction. Yeah, so typically you're moving along a horizontal line. The velocity, positive velocity means we're moving to the right, and a negative velocity means we're moving to the left. And the same thing, if we're moving up or down, a positive means we're going up, and a negative velocity means we're going down. Okay, and also then, so what is in speed is actually the absolute value of the velocity, because it doesn't really matter. I mean, we don't, if someone said, how fast are you traveling? You would just go, 32 miles per hour, or 30 miles per hour. You wouldn't go, I'm traveling at negative 30 miles per hour, right? So the whole concept of a negative velocity or positive velocity, this just gives us an idea. It's just this kind of, it gives us an idea of which direction we're going in. But but if if you're in a car and you want to see how fast you're going, you don't go, okay, well, I'm going east, so that means I'm going positive, and I'm going west, that means I'm going, the speed is negative. So yeah, we don't do that. So the speed is just the absolute value of the velocity. Okay, so now let's look at oh, this is kind of an interesting problem, example 2 here. Okay, so now we're moving along a straight line. So the thing is, so just think if you're like pacing back and forth in a room or pendulum, you're covering the same position over and over and over again. So, or like you're driving round trip from your home to work and back home. Well, at the end of the day, you're at the same position, but that doesn't mean you haven't traveled anything, right? So that's the thing. So we have this distance function here. In this case, at 1/3 t cubed minus 4t squared plus 15t plus 10. In this case, t is in minutes, and s is going to represent the position in feet relative to to the starting point. So it's 0, you're at 10 feet. Okay, so and so the problem says, how far have you traveled in the first 8 minutes? And the thing is, we don't want to. You can plug in, if you just plug in 8, you could not guarantee, but you're going to potentially get the wrong answer, because it's not taking into account that, see, remember, we're moving along a horizontal line. So that means, okay, we could be moving to the right. Let's turn around, let's move to the left. Let's say we're pacing back and forth, right? So, so S of 8 doesn't take into account the fact, you move to the right for a while, and then you move to the left for a while. So the one thing that's kind of important to note is that when we change direction when the velocity is 0. So yeah, so when we change direction, you kind of have to slow down, and then let's say, theoretically, let's say we're pacing back and forth. So we go, from one side of the room to the other, and we turn around. Let's say that's where the velocities are. We kind of slow down and we turn around, and then we start going the other way. kind of like, I guess, swimmers do when they're going back and forth in a pool. Not that I really know that much about swimming. Okay, anyway. So, okay, so let's find out where the velocity changes direction. Okay, so we take the, and we're gonna be doing this a lot in chapter 4. Okay, yeah, just coming attractions, something to look forward to. Okay, so we take we find the derivative of the distance function, which is 1/3 t cubed minus 4t squared plus 15t plus 10. And it turns out that, it's kind of set up nicely so we can actually find, t is in whole numbers. So the velocity, or the velocity function is t squared minus 8t plus 15, and you set it equal to 0. Well, it factors out nicely. And we see that we're turning around. We change directions at 3 minutes and 5 minutes. Okay, so so we start going to the right, and so from 0 to 3, the velocity is positive. Okay, and then at t equal to 3 minutes. Oh, the velocity is negative. So actually, we change directions. We start going to the left. And then at 5 feet, that's where the velocity is 0 again. We're turning around and we start going to the right. So I just want to emphasize here, the fact that the velocity, a 0 velocity doesn't necessarily mean we're changing directions. But in this problem, it does. Okay, we'll learn more about that in chapter 4. Okay, so anyway, so let's just finish this problem here. Okay, so we see that we have a positive velocity from 0 to 3, a negative velocity from 3 to 5 minutes, and then from 5 to 8 minutes, we have a positive velocity. So let's see, what is the value of the function at 3 minutes? And we've gone 28. It's 28. And then we actually look at, and then we're going from 28 feet, it's in feet. We're going from, and then at t equal to 5 minutes, the position function, it's actually because we're going to the left, we're actually closer to the beginning, right? It kind of makes it, see, at first it might be confusing. Oh, wow, at t equal to 3 minutes, you're at 28 feet. Oh, but now what happened? At t equal to 5 minutes, it's less. And that's because we've turned around and gone back to the left. Okay, so what's the difference there? So we've gone from 28 feet to 26.67 feet. So in the first 3 minutes, we've gone 18 feet. And then the next 2 minutes, from 3 to 5 minutes, we've gone 1.33 feet. And now, okay, so starting at t equal to 5 minutes, okay, we've turned around, we go back to the right, and at 8 minutes, you're at position 44.67. So what's the difference? How far have you gone from 5 minutes to 8 minutes? And you just take the difference. Oh, you've gone another 18 feet. And so you just add those 3 numbers up, 18 plus 18 feet, plus 1.33 feet, plus 18 feet, and you get about 37.33 feet. Okay, so, and there we had to take into account the fact that, we had to find out where we're changing directions. Okay, so what I said before, so here, a velocity of 0, we change directions. If you just have this function, like t cubed, let's say your position function is just t cubed. Okay, it's always, so you're going to get a velocity of, you can get 0 velocity, and the function can still be going up. So you're not actually changing directions. You can get something that's called a point of inflection. So in one case, the graph is concave down, and then it's concave up. We'll learn more about that in chapter 4. But again, so a 0 velocity can mean that a velocity of 0 mean you might be changing direction, but not necessarily. So that's all I want to emphasize. So, okay, so I think this is a good problem right here. I think this example too is a very interesting problem. Okay, so now let's talk about acceleration, and we'll talk a lot about second derivative when we start talking about optimization problems. Which I think is chapter 4. So the acceleration is the derivative. It tells us how the velocity is changing. So positive acceleration means that the velocity is increasing. And a negative velocity, again, a positive acceleration or positive second derivative means the velocity is increasing. And if the acceleration is, or the second derivative is negative, the velocity is decreasing. Okay, so let's just see here. So here's another velocity. I'm looking at this example 3. So there's another distance function, and it's let's say we have a rocket just yeah. So we're kind of launching some rocket off the edge of a cliff. Let's say it's about 100 feet above of the ground, and so the distance function is, let's say it's given by 4.9 t squared, where t is in I believe seconds, and the height is in meters, and so negative 4.9 t squared plus 80 t plus 100. Okay, so it says write the velocity and acceleration function. Well, that's the easy part, right? You just take the first and the second derivative of the distance function. Okay, so now here's another one. Okay, we're kind of getting a little bit ahead of ourselves, but when is the rocket at its highest point? Yeah, so that's where does the velocity go from positive to negative? Okay, and so you just find out where the velocity is zero. So when I say we're getting a little ahead of ourselves, what we're going to learn eventually that a zero velocity doesn't mean that we're changing direction. But for now, let's just assume that that's what's happening here. Okay, so you just solve for the velocity. Okay, so when is, and I think there's actually a problem in the homework similar to this. When is the velocity at its highest point? And so you take the you find the first derivative and you set it equal to zero, and you find where the velocity is. I think our intuition tells us that. So here, even though we haven't kind of gotten to the mathematics, oh, the velocity is zero, therefore it's changing the rocket's changing direction. I think our intuition tells us that. You throw a ball in the air, and where it's at its highest point, the velocity is zero, right? So the ball is going up and up and up, but it's kind of slowing down. The velocity is decreasing in magnitude, but it's still going up. And then what happens when it reaches its peak, okay, then the speed starts picking up, just kind of like a roller coaster as you go down. Okay, so the velocity is zero at about t.1, 8.1.3 seconds. Okay, so that's the time. That's the domain. So the velocity will become zero about 8.136 seconds. So the height, you just plug in this value here into this original function, and then you'll get the peak height is about 426.53 meters. And so then when does the rocket hit the ground? Well, now you just have to, you don't actually need calculus for this. You can use your calculator. I'm not sure this one actually factors nicely. So you just want to know when this function here is equal to 0. So you can just use a graphing calculator. And on the quizzes, I don't actually, you won't see any equations where you have to use a graphing calculator to solve the equation. And then, what is the rocket? So what's the velocity when it hits the ground? Okay, so we know that it hits the ground at using the calculator, we see it hits the ground at it's actually about 17.5 seconds. So you just plug that into the velocity. You just plug 17.5 seconds into the velocity function. And when it hits the ground, it's going at a negative 91.433 meters per second, but the speed is 91.433 meters. So if someone say, hey, how fast, what is the velocity when we hit the ground? You wouldn't actually put, if you were speaking, we'd be talking about the speed, not the velocity, right? So typically when you say how fast something is going, you don't, or the velocity, even kind of in casual language, we really are talking about the speed. Okay, I actually might, let's see right here. So this part I think is kind of interesting, the second part. So those of you who are looking at this file, I am actually going to skip this for right now. And this is something more from chapter 4.